Analyses. All right, so my thesis came out of the basic idea of brain-computer interface, which is that even if you can't move whatsoever, you can still control a computer. So it's an interface which hooks directly into the brain, and am I on the mic? Okay. So it's directly into the brain, and there's no physical interaction whatsoever necessary. And this is really important for certain populations who can't move. In particular, the extreme case would be locked-in patients who can't even move their eyes whatsoever. And we'd like to enable them to do things which might be considered useful, or some of them, there have been complaints. All right, is that better? Okay, I'm sorry. All right, so to reiterate, brain-computer interface, directly hook the brain into the computer, no physical interaction whatsoever is necessary. And next button. I'm sorry, but this is the arrow. There's another one. Oh. There we go. All right, so the very simplest idea of an interface is we have a one-to-one connection between a command and an action. So as long as we can be clear on what the command is and interpret that some way, we can have an action. It doesn't have to be one-to-one, but in the simplest idea, it is. And so I have a picture of the homunculus here, because this is the simplest demonstration that in the brain there is a distribution of different actions or thoughts in locations in the brain, or there's also different activation patterns. It's not quite as simple as this. We'd love to just say there was an action here, so have this action on the computer happen. In reality, there's a lot more work that has to go into it to find that out. But at least this is a clear thing that different actions in the brain are represented differently. And in particular for imagined movements, mirror neurons, there are mirror neurons along this motor cortex which simulate actual movements. So I can imagine moving without actually moving my own body, and a similar thing will happen in the brain. And we can use these to classify these specific movements for our interface. And we choose EEG, of course, because one of the main ideas of our framework is that we want brain-computer interfaces which can be used in the home. So we don't want $50,000 devices or multi-million-dollar devices that have to be run by a team of trained professionals. We would love something that could be set up just by a caretaker in the home in the matter of a few minutes, or kept on the head, and EEG is really the only feasible imaging device at this time for that. And in particular, we have this, the emotive epoch, which is just 14 channels, 128 hertz, and there's a lot of noise to it associated. It's not as good of a device as a scientific device, but we found it to be good enough. So it's about $300, which means it's affordable for someone in their home that they could use. It's wireless. It takes a few minutes to set up. You don't really need any training to set it up other than the basic idea of where things go. It doesn't have to be precise. There's no measuring along the scalp to correctly place the nodes. So we think this device is great for what we were using it for. And in general, sorry. So EEG in general has a pretty high noise level. There's a really high, it has great spatial resolution, which also means we have a lot of readings per second. 128 hertz over 14 sensors. It's a lot of stuff to do. So, and this is basically based off the BCI 2000 framework here, which is to say we get our data, we clean it up, we classify it, and we output it to the application. So here's a very simple picture of application where we would move a teapot to a target, right? Really simple, and we get more complex later. But the general idea of BCI 2000 is we can pick a module and we can run it with those modules. You don't need any programming experience to do it. So we might pick the common average reference over all the modules, which is the best one for our headset in particular and in a noisy environment. and maybe a machine learning classifier, which I've added several into the BCI 2000 framework, so we can use those and increase accuracy over time. The EEG data in particular looks pretty messy. So in here actually is someone thinking a command, but you can't see it. There's no way of knowing. In a lot of scientific studies, you'll see someone putting up an image which looks really clear, and you can definitely tell that there's a reaction or a command here in the EEG or the fMRI in one location. But in reality, on a trial-by-trial basis, especially with a device like the Epoch, which you can see where the sensor is located on this map, by the way, if anyone's curious, you just don't have that clear data. It's really hard to tell at the moment what's happening or when it's happening. And since our interface that we're interested in is asynchronous, meaning we don't want to say, do something now, then they have them do it, and then we classify what it is. We want at any time the user can say, I want to do this. They don't say they want to do it, they just initiate it by thinking it. And then we want that to happen, which means we're constantly classifying at all times. We don't know the onset or the exit of a particular command. And we're just looking at data like this. So a lot of typical methods aren't really sufficient for classifying this in real time, especially because a lot of the methods take a long time to classify. And we're looking at doing this in a personal computer as well. So if it takes more than 500 milliseconds, users are going to get very frustrated, and a lot of things aren't going to work as well for them. And so this is a basic interface I wanted to talk about, so if we use the common average reference, we would average across each node, subtract it from all of them, which would reduce a lot of noise from the interface. These were a couple of modules I wanted to talk about, excuse me. And if we reduce the noise from all of them, like the EEG headset, for example, the lights in a room, they're at 50 to 60 hertz, depending on your country. They're louder than the brain is to the headset. So we have to subtract that noise. If the user's moving, that's louder than the brain is, because the muscles along the head, if I smile, these things go crazy. So it's actually probably easier to use a headset with someone who can't move, because you wouldn't have all of those additional artifacts. But there's a lot of filtering that has to go on. In general, common average reference works because it adds over everything and subtracts the common average from everything. Not always. We can add in a couple different classifiers if we want. This is the example. And here once we have clean data, we have to take it into feature vectors for the classifier. The example here would be a fast Fourier transform where we divide it up by frequency into bins, and then we have those bins over time over sensors, which is a fairly large space, but for certain classifiers, that large space is okay. And one general example of a classifier, for those of you who aren't sure what it is, the bottom right here has a linear classifier, 2D. Nothing we have would actually look like this, but the basic idea is if you want to divide between the red and the blue, you'd put a line between them so that there's maximum distance between them. And then if a new one comes in, you'd say which side of the line does it fall on, and that would be your classification. Linear classifiers do work okay for EEG data, but they're not very flexible, and your data isn't always linear. And if it's not linear, these don't work. So one of the other things we've implemented is a multi-layer perceptron, which is based on the artificial neural network, and it looks something like this. This is actually a computer scientist interpretation of what a neural network looks like, more or less. So if you imagine each of these nodes in the middle as like the soma, each neuron adds into everything on the next layer to it, and there's a weight between each of them. So everything goes from one layer to the next, and there's an activation function in each soma determining whether it'll be active or not. So one example, in a neuron, it's sort of on or off, right? In this case, we could do sort of a log function, like a continuous log sigmoid function over each soma. So we have sort of a continuous activation function, and this goes from one to the other. And the important thing about these artificial networks is we don't actually know what they're doing. We can see the weights in the network at any time, but we don't really know what it means. We just know at the end what it's outputting. In our case, this network would output, say we have 4 output nodes, that would be the confidence from 0 to 100 of each of the possible outputs. So we not only know which option it thinks is the best classification, we also know how confident it is. So if they're all very low confidence, we could assume just nothing's being done. and then we wouldn't classify or move the interface whatsoever. Right, so once we have those classifications, we can actually feed them into the, wrong button, into the output application. And the application, we've built one into the system. We could also pipe the output into another program, like a 3D design program. In this application, again, we have our teapot, which we'd like to move. And simple 1D along one line. So that's important later that we see we have this initial one dimension. But our environment supports movement in 3D, and it supports the three basic elements of moving an object. So translation, moving it around, north, south, east, west, or whatever your frame of reference may be, rotation and scaling. And with this, we can move objects around in a space and place them and keep them somewhere. And so one of the biggest problems with the asynchronous design is actually training the MLP, the multi-layer perceptron. Because if we just put a person into this thing and they can move freely in any dimension they want, we don't know what action they're doing or when they're doing it or how to classify it. So in this case, we actually have to train the user and the machine learning algorithms at the same time. So that's why we bind it to one dimension to start with, and we know which action they're thinking of over discrete time periods. And in this way, we're training the user how to imagine these things. We have a simple linear classifier running at the time, so they do get some biofeedback from it, which actually deviates their responses even more and makes it easier to classify. And then we can feed that input into the MLP, and then we get a better classifier in the end of it all. In testing, we'd be testing the MLP and the user here as well, but we can open up the other dimensions of the environment and have the user move around. It's harder to test things here because we don't know exactly what they're thinking at any one point in time. They might be correcting and going the opposite direction than we think they are, but that's up to them. And self-reports don't work very well here because we're looking at timing in milliseconds, not in seconds. So it's hard to really know exactly when they're doing something. So we can only measure things like general timing or pathfinding. If we put obstacles in the way and they have a target, then how close do they get to these obstacles? Do they go all the way around? If you look at users using a mouse or something as a control interface and they have an object, they're very likely to just give it a big loop around. But that's not so much the case with this brain-computer interface because it's really hard to do. It's really hard to think of an action and only that action. So we actually see deviant behavior between these different control interfaces, which, I wanted to reiterate, this is not a programming exercise. This is a framework we've built which is then entirely module, and this is just what it looks like. Kind of you'd add in preferences, you'd add which modules you want, and you'd run it. It's not something you would have to program or understand even how the networks work if you wanted to. And so in response to deviation of behavior, we saw some interesting things. I intentionally don't have any statistics up here because my project is pretty new. I'm a pretty new grad student, and we don't have enough hard numbers that I wanted to put anything up and say. So this is mostly subjective based on what I've seen from a few test subjects running in these experiments. And most importantly, I think, is does using this interface change the way you design things? So from what I've seen, if by using this different interface, designs actually look different. People, the couple of subjects who've done it, tend to make very utilitarian spaces. So if you have a kitchen or something, then things are lined up next to each other by use along the walls in very simple configurations as you might find in a very basic kitchen. Whereas if they have a mouse and keyboard that they're more familiar with, it's much easier to use. You're more likely to see these more creative outlets that are a bit different than expected. And there's a couple other things, like I really want to extend the module into drawing sort of line-based applications for potentially making blueprints and expanding those into 3D or other objects, but those are future work along the way. In the meantime, I'm really interested in looking at how using the brain interface affects design or planning, because you do have this sort of mental thought of how you're going to do things, which is not the same as this mouse keyboard movement, which we're all so used to doing and doesn't really interfere necessarily with our cognitive process about it. So I think that's about the time I have, so I'll just go to questions.
There's time for questions. Yes. Anders?
Yeah, I have a question. Speed down. Thank you. I was very interested in that you seem to be capturing the thought impetus before the actual activity is activated by the muscle space. Is that right?
Yeah, usually.
And,
I mean, it's about the same, but the muscles will have a delay. If
Right.
nothing else, just for it to propagate down. But
So that's one of the things that's unique about this. What's puzzling me, though, is as you said, there are going to be other thoughts clouding. And I wonder if maybe that then becomes an experiment in itself. In other words, puppies, photos of puppies at the same time that you're drawing something to see what kind of clouding is actually occurring.
Right.
Otherwise, it's just randomized.
yeah, that is actually one thing I wondered about. And in the last slide, I mentioned like affective states. And the emotive epoch ships with this affective state sensor thing, which may or may not be accurate, but pretends to display what your affective state is at the time based on the EEG. And I would be very interested in seeing if affective states change things, or just whatever else is going on in the environment as a distractor. Because certainly, if you're distracted, so the test subjects who are running, one of them was up between 92 and 95% accuracy on here, which for VCI with this headset was really good, just in the four command modality, so not 8 commands like the state of the art or whatever. But with 4 commands, he was doing pretty well. But the moment anyone started talking to him, it just drops way down, almost to 50% or something, which is still significantly better than chance, but he really needed to concentrate on it. And it's possible that over time, as he learned and got better at the system, he might be able to do it while distracted, or while something else is on there in a different affective state. But
Have you thought about translating the signals that you capture out of the brain, which sort of precursors to the muscle phased space? Have you thought about actually extracting those things and having those activate themselves in a separate robot?
oh,
In other words, I think that mechanism will move that pot to that picture of the pot.
that would be pretty interesting. Yeah, the problem is we'd only have about 4 actions, so we could do the cardinal directions as long as the robot had, the interpretation module to say forward and just walked forward. And there's some animal studies I know where they've sort of linked the neurons more directly, and I think it'd be possible. What I really wanted to do actually was hook it up to a Roomba, and so I could go around and vacuum myself. But
Actually, there are a number of people working on premotor cortex to command prosthetics, right? People who've lost an arm, they learn to move a robotic arm by training the premotor cortex so that the movements become sort of canonical. Yeah, that's nice. But you need more degrees of
yeah,
freedom.
those are usually with embedded sensors, right?
You can do it with embedded sensors better than you can with...
Yeah, I don't think this headset would have the accuracy or
you're
ability to do it. Maybe, but it would have to be done.
There
Yeah.
are also people who are working on, getting evoked potentials to give you timing signals so that you can actually cue in particular things. So you can look actually for 300 millisecond delay and then dwell on that particular set of signals as opposed to continuously filtering.
Yeah, that's one of the things I was thinking of adding on to this, but I hadn't quite gotten it working yet, so.